carbonyl, we can deprotonate the alpha carbon, creating a carbanion. The negative charge here, as it tries to drift, makes it easier to remove a hydride ion from the beta carbon. And since FAD can accept the hydride ion as a 2-electron carrier, right, we can reduce FAD to FADH2.
Did you say that's membrane linked and FAD?
Yeah, okay, so
It's
this enzyme, like succinate dehydrogenase, is also associated with the mitochondrial intermembrane surface. But it's different from succinate dehydrogenase in that succinate dehydrogenase was an integral membrane protein, right? It had a part, a coenzyme Q part, that was buried within the membrane. This fatty acyl-CoA dehydrogenase is peripheral in that it interacts with this one. And let's see. This protein is called the electron transfer protein that acts as a go-between. Where succinate dehydrogenase could, because it was integral itself, transfer electrons directly to coenzyme Q. This electron, what do I call it? Electron transfer, what's the F? My F locked up. It's not, F isn't protein. Somehow F and protein.
That's what you said.
Hmm?
You didn't give an F earlier. You just said
What was the F? Dang it, I always forget my F on this. Anyway, this is reduced by the FADH2. This is a 1-electron system. So it can act as a go-between to take the FADH2, take 1 electron at a time, and use that. There's a second protein which ultimately reduces coenzyme Q. So, like succinate dehydrogenase, it creates an alkene, it uses FAD to do it. What's different from succinate dehydrogenase, where succinate dehydrogenase has an integral part of the enzyme that can interact directly with coenzyme Q, this needs help, right? It needs this protein, electron transfer factor. Factor is F.
It's flavoprotein.
Flavoprotein, thank you. Thank you. Electron transfer flavoprotein. I always forget my F. Okay, so we have to have these to link the peripheral acyl-CoA dehydrogenase with the reduction of coenzyme Q within the core of the membrane.
And there's 2 different ones.
Yeah. Okay. This protein acts as a go-between there are a number of other FAD utilizing dehydrogenases for other systems that also go through this intermediate. So this system lets a number of other peripheral FAD-linked dehydrogenases feed their electrons into coenzyme Q. Okay? So we get sort of succinate dehydrogenase developed as a specialty protein. For the other similar reactions, we developed systems to develop this general linking system between a number of dehydrogenases in the matrix to get the electrons to coenzyme Q. Does that make sense? Devin's thinking about it?
No, it makes sense. It makes sense.
Okay. Are we happy with that? Oh, let's see. That's FAD there. Let's see what we want to talk about. Okay, so the catalytic mechanism of the acyl-CoA dehydrogenase, right? We mentioned this. This is a Dr. Burnell slide, right? Obviously, this was not one from your book. But I was all excited about another example of carbanion chemistry. So this is what I said verbally when we were talking about this, right? There is, what is that? What amino acid is that within the protein?
Aspartic acid? Glutamic?
Glutamic, yeah, right. So there is a glutamate that acts as what kind of base? A general base, deprotonating the alpha carbon, right? We deprotonate that alpha carbon, create a carbanion. As that tries to find something to share that with, I mean, we get the resonance, but it can go this way. The hydride can be transferred to FAD. The electrons can move, and you can get a stabilized anion intermediate of FAD in the alkene form, the alpha-beta unsaturated fatty acid. Yeah?
What makes it favorable to create that double bond instead of bumping the electrons up to the O and sharing them with
Well,
the alpha?
it can do that, but in part, the FAD, the chemistry is set up so that the energy created by this is enough that it creates the potential to reduce that. Plus, remember what ultimately happens to this FADH2. Well, it's already reduced. It gets reoxidized, and so what's ultimately doing this, even though we have this as an equilibrium reaction, this product, since it gets reoxidized, pulls this reaction this way. Even though the equilibrium would be unfavorable under standard conditions, by removing that product, we make it favorable.
Okay.
Okay? That makes sense? Okay, so next. Right, are we happy with our dehydration? So we just spent 15 minutes talking about one step. Now, we're going to, when we go from there to there, what do we do?
Hydrate.
We hydrate. We, oh, come on, I make this joke every time we hydrate. Just add water, right. Right, the boat place on the east side. Just add water. Every time. Okay, so someone's getting a free commercial. So we add water, but given that we are adding water across a carbon-carbon double bond that is conjugated with a carbonyl group, what do we expect about this addition of water? What gives it this specific regiochemistry to pull the organic chemistry of the day out?
The enzyme.
Well, one, the enzyme probably does direct it that way. But what about the chemistry would, I think if we did this in solution, under proper conditions, we would get the same result.
When the water adds to the beta carbon, it'll be a carbanion again.
Right. The water adds to the beta carbon to create a carbanion on the alpha carbon. What kind of reaction is that when we get a nucleophilic attack on the beta carbon to make a carbanion on the alpha carbon?
Michael?
What? Go ahead.
This is Michael addition.
Michael addition, yeah. So, right, Dr. Stickney can be excited because we're going to do a Michael type addition. And so this is another slide that I put together showing, let's see, apparently this is glutamic acid day, right? Because that's another glutamic acid. So here's a glutamic acid pulling on a water molecule, right? Here is our fatty acid, right? Here's our sulfur of our coenzyme A. Here's the carbonyl. Here's the alpha carbon. Here's the beta carbon. This is a phenyl ring so that it would bind but not react well so that they could do X-ray crystallography. So they put a phenyl ring as the gamma carbon, right? And so here is our water positioned to attack the beta carbon, and as the electrons shift to the stabilized carbanion position, the water can then itself act as the acid to protonate that. So you get a conjugate addition across that carbon-carbon double bond, and we get that 3-hydroxy fatty acyl-CoA. Right? And so this is where we, what do we call this whole system? Fatty acid beta oxidation. Well, if we look at that beta carbon, in these two steps, it's gone from saturated to being an alcohol. And so the beta carbon is ending up the one that looks like it was oxidized. Does that make sense? So, any questions about that? Comments or complaints? Did I really go through the whole thing and never write on the board? Okay. So we should be able to finish this easily Monday. Talk a little bit about how do we deal with unsaturated fatty acids. And then I hope we can get to cholesterol by Wednesday. Cholesterol synthesis.